Welcome to the Photovoltaics or Solar Electricity section of Introduction to Renewable Energy. In this section we'll be talking about solar electricity. Literally, photovoltaic means photo or sun, and voltaic for electricity, meaning electricity produced by the sun. In the early 1950s, Bell Laboratories developed the first silicon-based solar cell, which would ensure that many generations could use solar electricity, as silicon is the second most abundant element on the surface of the Earth. In this section, we'll discuss how photovoltaics work, system components, system types, the solar resource, and barriers and benefits to solar electricity. So how do photovoltaics work? Photovoltaic or PV cells are generally constructed of two thin layers of silicon. The top layer is made of a silicon phosphorus impurity mix, and the bottom layer is made of a silicon boron impurity mix. While this is very technical, the important thing to note is that the top layer's components create an overall abundance of electrons, and the bottom layer's components create an overall lack of electrons. As we discussed in the first section, imbalances in electrons make them want to react, and electrons want to travel in the path of least resistance. The atoms in the PV cells are unbalanced, and they want to react. As sunlight strikes the solar cell, it goes straight to the bottom layer, knocking an electron loose. The electrons travel toward the path of least resistance, so it travels to the upper layer, where there is already an overabundance of electrons. The electrons won't try to attach to those atoms, and instead they find the conductor and travel through a circuit. From the circuit, it will go through a device to a load, powering that load. After it powers that load, it comes back to the cell through the conductor attached to the bottom layer, finishing the circuit and attaching to an atom in the bottom layer only to be knocked loose again by the sun. This particular cycle takes place billions of times per second. A collection of cells wired together creates a module. A group of modules wired together creates an array. The number of modules you will need in an array will be based on your electrical usage. This is why it is important to follow the sequence of sustainability and first make reductions through conservation and then through end-use efficiency before you buy a PV system. This will save you lots of money in the long run. Modules are modular, which means that you can add more as you go. If you only have enough money for a few modules now, but want to have a larger system later on, you can just add more when you're ready. In this animation, we're going to take a closer look at what happens inside the solar cell when the solar radiation strikes a panel. Here we see just one electron's path across the process. The electron is knocked loose from an atom within the solar cell. It travels through the p-n junction, which is the black bar in the middle, and forced up to the top layer. In the top layer, it doesn't find an atom to latch onto because of the overall abundance of electrons in that layer. Instead, it travels toward the path of least resistance, which would be the conduit and battery shown as the load in this case. After powering the load, it returns to the bottom layer of the solar cell, only to go through the process all over again. As with all systems, the system components vary widely. But again, essentially, the system is divided into two parts, the array and the balance of system, which is all the other parts of the system. The balance of system components for a photovoltaic system can include a charge controller, batteries, inverters, disconnects, combiner box, lightning protection, meters, appliances or loads, and the owner. To reduce the cost of the system, the balance of system components should be placed as close to the array as possible. The balance of system components depend largely on the type of system that you want to install, but some components will always be present. The appliances or load are a big part of the system. Energy efficiency measures that increase the end-use efficiency will really improve the system. For every $1 you spend on energy efficiency, the general rule is that it has $3 to $5 return on the reduction of the system cost. The owner is always the most important part of the system. There is no maintenance-free system, so the owner has to be involved and pay periodic attention to the system. If you don't check the oil level in your car, you most likely won't check the water level on your batteries, which means you should probably think about doing a batteryless system. If you know you don't want to go out and physically change the angle of the racking of a system periodically, you'll probably want to look for a fixed tilt angle rather than a variable tilt system. There are four main types of systems in photovoltaics. They are PV direct, standalone, also called off-grid, utility interactive, also called utility intertied without batteries, and bimodal, also called utility intertied with batteries. PV direct systems are the simplest type of system with the least amount of components. PV direct systems consist only of a PV module or array and a DC load. This would be a good application for a pump of some sort. When we were talking about the PV integration in solar thermal systems, this is the type of system that would be. When the sun is shining, the load receives electricity. When the sun is not shining, the load will not work. A standalone or off-grid system is a self-contained system. Standalone systems are usually used when the utility power lines are not in place and it would be more expensive to bring the utility in, or when a homeowner wants to be completely independent from the utility. A standalone system includes the following components at a minimum: an array, charge controller, batteries, inverter, and metering. The charge controller protects the batteries from becoming overcharged and measures the battery voltage. Batteries are the storage tank for the DC electricity produced by the panels to be used at a later time when the array is not producing electricity or when electric loads are greater than the array production can supply. With a standalone system, you would have complete energy independence and no utility bills. You would need batteries, which are expensive and do take maintenance. You have to maintain fluid levels and charges, and you periodically have to overcharge the batteries to loosen the lead buildup. The system has a large balance of system footprint since it has so many components. And if you wanted to run loads on days with little or no sun, you would need a backup system such as wind, microhydro, gas, diesel, or biodiesel veggie oil generator. Wind is a perfect companion backup. A utility interactive or utility intertied without battery backup system requires the least amount of attention from the homeowner. It is the least expensive, with the exception of the PV direct system, and has the least amount of maintenance. This type of system puts clean energy onto the grid. Your excess power, instead of going into the batteries like in a standalone system, is stored on the grid as a credit. This system is only as reliable as the grid, and when the grid is down, you don't get any electricity through the PV system, though it still may be able to produce it. You would not want to install this type of system if your utility grid is unreliable. A utility interactive system includes the following components: an array, inverter, disconnects, utility interconnection contract, and any additional components your utility may require. A bimodal system is the best of both worlds. You still get electricity when the grid is down. You can put clean energy on the grid. You can store excess power in the batteries, but when they are full, you can store the excess on the grid as a credit. This system has batteries and the associated maintenance. It is the most expensive system with the largest balance of system footprint. The bimodal system includes the following components: an array, charge controller, batteries, inverter, disconnects, metering, utility interconnection contract, and any additional components your utility may require. Again, we want to optimize the performance of our system, and the same rules that apply to the solar thermal system apply here when it comes to the solar resource. We have to pay attention to the sun's seasonal changes to optimize the performance. We need to have our array mounted at an angle to the sun that will maximize their performance and be in the direct sun with no shading from 9 a.m. to 3 p.m., aka our solar window. Unlike solar water, you need to pay much more attention to shade with a PV system. The cells in a PV system are wired together, which means that one cell shaded reduces the productivity of the whole. If one cell is shaded, it could actually reduce the productivity by 50% depending on the cell. If the entire bottom of a module is shaded, it could reduce the productivity to 0. For this reason, and because a PV system is more complex, it is vitally important to get a site assessment done by a professional. A site assessor will look at the efficiency measures that could be taken into account. A PV site assessor is trained to decipher the solar window at your site, your specific electrical needs, and possible shading considerations. The site assessor can advise the right type and size of system for your site determined by your budget, your wants, and your site's features. The site assessor can also explain to you your options for mounting styles and aesthetics. PV arrays can be building integrated, flush roof mounted, rack roof mounted, awning mounted, ground mounted, or take advantage of trackers that will follow the sun. Most of the barriers to PV have to do with misinformation and unrealistic expectations. You've taken the first step in dispelling some of these by taking this primer course. Another barrier is the installation of unreliable systems. Make sure when you start the process of installing your system that you are getting proven systems installed by experienced professionals. The North American Board of Certified Energy Practitioners, or NABCEP, certifies PV installers so you know that they have experience. The environmental benefits of PV are obvious. For every pound of coal burned to produce 1 kilowatt hour of electricity, 2 pounds of carbon dioxide, 1/100th pound of nitrous oxide, and 86,000th pound of sulfur dioxide are put into the atmosphere. In a year, the average home will consume 12,000 pounds of coal to produce the electricity it uses. That's it for this section, but if you want to know more about solar electric systems, you may want to check out some of our other courses. Two courses that may be of interest are PV 050, Primer on Solar Electricity, or PV 101, Basic Photovoltaics. If you're interested in installing your own system, you'll want to have your site assessed by an MREA Site Assessor Certificate holder. You can find the list of site assessment professionals at www.mreacsa.org. In the next section, we'll be discussing wind electric systems.